The technique of drilling and fracturing. So I repeat, I'm going to show you snippets of a movie. A couple of reasons. Seeing something in action is better than just seeing a cartoon. A lot of what's in the movie is perfectly accurate, and it gives you a better perspective of the actual drilling and fracturing process. Some of the stuff in the movie is inaccurate, and I'll try to point those things out.
Let's take a look at the horizontal drilling and stimulation processes that have made shale exploration so successful. A drill bit is mounted on the end of the drill pipe. As the bit grinds away, compressed air is pumped down the drill pipe to flush rock cuttings from the hole and lift them to the surface.
Notice that while that's happening, what we have is what's called an open hole situation. There is no cement, there's no casing, you only have the drill string, which is drilling a hole in the rock. And initially that hole is maybe 18 inches in diameter, and then you go down and it goes down to 12 inches in diameter, and then down to maybe 8 inches in diameter, and ultimately something like 5 or 6 inches in diameter. But while the drilling is going on, you have open hole. So that drill string is going to, in this movie, pass through the water table in a minute. Okay, and when it does, you've got to imagine, let's see, in that there's either compressed air or drilling mud, and I'm drilling through the water table, and there's nothing between the water table and the drilling mud or compressed air. Oops, but that's always true. It doesn't matter whether you're drilling a water well, a conventional gas well, an oil well, or an unconventional gas well. While you're drilling through the water table, you are poking around in your water. And you're liable to have whatever is in that hole get into the water table. So that's the common problem that we see every time you drill a well. People who are downstream of where you're drilling are liable to get muddy water in their well. And if they're using if they're using drilling mud, which they sometimes do instead of compressed air, then elements from that drilling mud will also go into the groundwater. That's unavoidable. No one has ever invented a way of drilling through the water table without drilling through the water table. Okay? So it's a problem. It's always existed. It will always exist.
Similar to a vertical well, the
Water
hole
table
is drilled to just under the deepest fresh water near the surface. The drill pipe and bit are then removed. Surface casing is inserted into the drilled hole to isolate the fresh water zone and also serves as a foundation for the blowout preventer, a safety device that connects the rig to the wellbore. Then, cement is pumped down the casing and out through the opening of the shoe at the bottom of the casing. It is then forced up between the casing and the hole, sealing off the wellbore from the fresh water.
It's important to understand here that when you drill the hole, the diameter of the hole you drill has to be larger than the diameter of the casing. It's kind of hard to push a steel pipe through a hole whose diameter is roughly the same as the steel pipe. The hole has to be bigger, usually 3 inches in diameter, which means this cement is on the order of 1 inch thick. So the so-called annulus that you've heard so much about, the cement problems, the bond problems between the cement and the casing, or the methane or frac fluid migration through the cement, it's important you understand the scale of things here. So if this is 8 inches of steel diameter, okay, that's 1 inch of cement. And that cement has to completely fill that annulus, otherwise you have the possibility of migration. That's a problem that's been around since this drilling process was invented back in the early 1900s.
The cementing process prevents any contamination of the freshwater aquifers. The pipe and bit are lowered back down the hole to drill through the plug and cement, and continue the vertical section of the well to approximately 500 feet above the planned horizontal leg. This depth is called the kickoff point, where the curve will begin so the horizontal section can be drilled. Up to this point, the process is the same as drilling a vertical well. Again, the pipe and bit are pulled out of the hole, and a downhole drilling motor with measurement while drilling instruments is lowered back into the hole to begin the angle building process.
And that is a miracle. This is the directional drilling miracle I told you about. How do you drill a hole that doesn't go How many people here are carpenters? Would you like to have the opportunity to drill a hole while you're making furniture that goes around a corner? Okay, and measuring while drilling, this is the electronic revolution. How do they know where that is? It's 5, 6, 7,000 feet down. How do they know where it is? No, because satellite can't communicate with what's down there. It's all electromagnetic communication through the rock itself. The rock is very conductive to certain wavelengths of electromagnetic radiation. So if you were ever in a doghouse, no. Am I talking to the husbands and fathers here? Or the doghouse is the place on the drilling rig where the guy is controlling this process, and he's got an LCD panel screen, and he can actually, this is what he sees. It doesn't look like a cartoon, and he's getting constant signals from the electronic device down here that goes through the rock and tells him exactly where that is to within a few inches. And then he can control the speed and the angle that motor has. The drill string is not turning anymore. The only thing that's turning is what's down here. There's a motor down there that's being driven by the pump fluid pressure. It's a hydraulically driven motor that turns just this part. This is just following along for the ride. So it's the idea that you're turning the whole thing. No, you're only turning the stuff on the end, and that's why you can turn.
The distance to make the curve from the kickoff point to where the wellbore becomes horizontal is just under 1/4 mile. Once the curve is completed, drilling begins on the well's horizontal section, called the lateral. The pipe used to drill the well measures 30 feet in length and weighs approximately 495 pounds each. It takes over 350 pieces of pipe weighing nearly 87 tons to drill a 10,500-foot well. At various stages of drilling, the pipe is taken out of the hole for tool and bit changes and put back in. This process is called tripping pipe. When the targeted distance is reached, the drill pipe and bit are removed from the wellbore one last time. Production casing is now inserted into the full length of the wellbore. Cement is again pumped down the casing and out through the hole in the casing shoe, forcing the cement up between the casing and the wall of the hole, filling the open space known as the annulus. Casing the well is a very important process because it permanently secures the wellbore and it prevents hydrocarbons and other fluids from seeping out into the formation as they are brought to the surface.
At that time, the drilling is completed. When you read on the DEP website that a well has been drilled in this county, that's what they mean. That part of the process is done. It does not necessarily mean that Schlumberger or Halliburton are now going to show up, or BJ Services, and do the next step, which is the fracturing. In fact, I heard recently that a large number of the wells that have been drilled in Pennsylvania have not yet been fractured. Well, why not? Gas price is too low. No infrastructure to process it, no infrastructure, no gathering lines to take it to your transmission lines. But on the other hand, and no place to put the wastewaters, and on the other hand, if you do the drilling, what have you done to the lease? You've executed it, right? You've locked up the lease. So typically, on the pads I've been on in Pennsylvania, you'll see a vertical well that was used as an exploratory well to make sure everything was hunky-dory, and the computer models that they're going to use to predict how all this is going to go on are fine-tuned, and then they'll come in and drill 1 or 2 horizontal wells and go on someplace else and shut those wells in. They'll come back later to do the fracturing to start producing the gas. So it's not necessary that they immediately go to this next step.
At this point, the drilling rig is no longer needed. A temporary wellhead is installed and the location is prepared for the service crew who will perf, frack, and prepare the well for production. The first of these steps is to perf or perforate the casing. A perforating gun is lowered by wire line into the casing to the targeted section of the horizontal leg. An electrical current is sent down the wire line to the perf gun and sets off a charge that shoots small holes through the casing and cement, and out a short distance into the shale formation.
This is what I referred to before as a frac stage. This might be 1 mile or 2 miles in the lateral, but they're only going to frac 500 to 1,000 feet at a time.
The perf gun is then pulled out of the hole. Next, because the shale is tight or compressed, the well will have to be fracked. Known as hydraulic fracturing, this is a process where water, sand, and lubricants are pumped into the wellbore and down the casing under extremely high pressure.
Some of that is true, some of it isn't. Or no, some of it is true and some of it is incomplete. So it's not just water, sand, and lubricants, but it is done under high pressure.
As the mixture is forced out through the perforations and into the surrounding rock, the pressure causes the shale to fracture.
Okay, last part of the movie I'm going to show you, because this is the part that irritates me a lot, because this is right in my wheelhouse. This is what I did for a living for Schlumberger for 20 years. These dead trees in winter, that's artist license. That's not what's going on. What's going on is what they don't show in this movie is that the shale is already fractured. You saw the images of the fractures? And what they're trying to do is force the fluid into those existing fractures. There is some additional fracturing that goes on because they can never perfectly line up every one of those perforations with an existing fracture. They can't do that. So some fracturing goes on, but as soon as the fracturing that does happen meets a joint, that's a weak plane, and that's where the fluid's going to go. So you don't get this shattering effect like a big explosive going off down there. So that's not quite right. It's also not quite right that all this happens to end. It might not. It's a very complex mechanics problem. I have a PhD student who's going to be defending her thesis next Monday, and it's exactly on what happens when a crack approaches a bimaterial interface. Ooh, heavy words. Material A, material B. This might be a sandstone, a shale. This is probably a sandstone or a limestone. They have different properties. And the joints don't necessarily line up. And this is the interface between them. So when a crack gets there, it has a bunch of decisions to make. It can stop, or it can go on through, or it can deviate and deflect and then go on through. All those wonderful things can happen. Those are things that do happen. So the movie is not quite complete. But you get the idea by now? Okay, this is how it works. All right, so now that you've seen the cartoon and you've seen a still cartoon and a movie cartoon, I'm going to show you the real thing. Okay, so now we're in what did I know and when did I know it? Contrary to what you think right now, I'm not as young as I used to be and look, but way back when I had all black hair and a lot of it, I went on my first sabbatical. That's the boondoggles that professors get every 6 years, you know. I wasn't boondoggling. I went to work in the unconventional gas program at the Lawrence Livermore National Laboratory, one of the weapons labs out in California. And there was an unconventional gas program funded by the Department of Energy. So we've known for a long time that there was gas in the shales out here. Okay? And we were working on it back then. So I'm going to show you some images from the research and development I was doing there for a couple of reasons. One, to show you that the problems we're facing today are old problems, not new. The industry has known about them for 25 or more years, and they're still problems. They're gradually being addressed, gradually being solved, but they're not solved problems yet. That's my point. Okay, wrote a bunch of papers when I was out there. Here's one from 1987. This is extracted from that paper. Considerable quantities of natural gas are locked tightly into the eastern Devonian shales. In those shales, the gas is mostly drained from the natural fractures, which tend to be vertical and spaced a few meters apart. To recover the gas, it is necessary to stimulate the rock reservoirs. That's using hydraulic fracturing. And rock reservoirs already contain natural fractures, and this makes it difficult to predict the effects of induced fracturing. So we set out on a research program to try to understand what those difficulties were and to try to quantify them and see if we could use computer simulation and knowledge of the rock to figure out how best to conquer those problems. Okay. How many people here have ever done finite element analysis? Okay, how many people here have ever used a supercomputer? How many people have ever done computer simulation of complex fracturing processes? All right, I'm really proud of this picture. It's from a 1987 paper, and believe it or not, the computer we used to do the analysis I'm going to describe was at that time the single most powerful computer in the world. It's about as powerful as the computer in my cell phone right now. But anyway, here's the picture. Here's a well bore, right? Here's the casing. Here's the cement. This is the rock. Every one of those lines is a joint, a pre-existing fracture. And we ask the computer, what happens if we inject a certain amount of fluid at this point through a perforation? And I'll show you a picture of a perforation in a minute. It goes through the cement, fractures the rock, gets into the first joint, and it has a decision to make. Do I go left or do I go right? Well, depends. Depends upon the pressures and stresses in the rock, depends upon the characteristics, the flow characteristics of the joint, the permeability of the rock. And so the computer model says, well, it all went this way, but when it got here, this is Main Street and Elm. It has to decide whether to go left, right, or straight, and some of it went that way, so you got the point. What we have is a network of flow fields. It's like a traffic pattern, right? If 100 cars leave this street at this time, where do they wind up? When they all have opportunities to make left turns, right turns, or go straight. The problem here is that this wound up being an unpredictable problem. We concluded in this paper that it's nonlinear chaos. What that means, for those of you who don't know, wait a minute, you told me these people all, no? They don't know? Okay, a characteristic of a nonlinear chaotic problem is this. A slight change in any of the conditions in the problem results in a big change in the answer. That's not a good position to be in. It makes your computer models virtually useless. They're fun, and you write papers about them, but they're not practical. So we couldn't use this computer model to tell Schlumberger where the fluid was going to go. And that's generally true. Okay. Fast forward 5 years, still working for Schlumberger, but now we're doing actual physical testing. Schlumberger had a computer model that would predict how every one of those perforations, boom, remember those little perforations you saw in the movie? Each one of those perforations spawns a crack. And Schlumberger had a computer model that said the cracks should start at this location, at this time, and take this shape and propagate this fast. Let's see how good the computer model is. That's called validation. It's a very important concept in engineering. Anybody can write down an engineering model or theory, and it's worth nothing unless it can reproduce what you can see. That's called the validation process. So it's always necessary to do physical experiments to show that your computer models have merit. So we drilled a hole, just like the movie said. We put a casing in it, steel pipe. We cemented the casing. We perforated the casing in the cement and the rock, and then we injected colored fluid as pressurizing hydraulic fracturing fluid to see how the cracks evolved over time. So here you go. There aren't very many people who have ever seen these things. We broke open the rock when we were done. So we broke open this big piece. And here's the casing. This gray area is the cement. Okay. These pink colored areas are fractures, natural hydraulic fractures. That hole is a perforation. Here's another one here. Here's a perforation in the cement. And there's the overall picture, and what we found out was that the computer model said that the cracks should all be semicircular or elliptical, and they should all propagate at the same rate, and we should have a symmetric result, and we didn't. But that's because we're working in a natural material, where there are variations in the properties point by point. That wasn't man-made sandstone, it was natural sandstone. So even though we could control in a laboratory all the pressures that we were applying to that block, we were squeezing it in 3 directions with the same stresses that would exist downhole. We still didn't get results that perfectly matched the computer models. Close. Okay, so computer models say that, and that's what we got. Reasonable. But that's just to show you that I work with Schlumberger. Okay, Schlumberger is still working on the same problem. I'm really proud of some of my students who went to work for Schlumberger and Exxon. And one of them once got the cover of a magazine which is very famous. It's called the Journal of Petroleum Technology. If you're anybody in the oil and gas industry, you want to get published in this journal, just so you know. Okay. So I'm not bragging that we got the cover, although that's quite an accomplishment in 1989. What was funny to me and ironic today and relevant to you as residents of Pennsylvania who hear things about methane migration, and frac fluid migration is that that's not a new problem. So when I went to scan this cover, I put this magazine in my scanner, and before I closed the scanner, I looked at the back cover. And I'm going to show you what the back cover is. It's a full-page ad from Schlumberger. Gas migration control, a comprehensive approach. Here's your casing, here's your cement. If you got migration through the cement or along the cement bond line, you call Schlumberger, and they bring out the golden fingers. And they squeeze that cement shut so that the migration is cut off. How's that for humor? Pretty sick, huh? Anyway, the point I'm making here is this is an old problem, and it will never go away. It is impossible to guarantee in any well, whether it's a water well, conventional gas well, oil well, that your cement job is ever going to be perfect. There's just too many complexities involved. Witness what happened in the Gulf of Mexico this summer. That's a multi-billion-dollar well, and they fouled it up big time because they had a faulty cement job for many reasons. Okay, so that's 1984, 1989. You might be thinking Ingraffea is getting kind of long in the tooth. Maybe he's been out of it too long, and by now they've solved all these problems. I want to convince you that they haven't, but they're still working hard. So here are a couple quotes from papers. Here's a paper from 2008 by this is the Society of Petroleum Engineer. This is a well-known guy who works for a well-known company. This is from his paper. I'll let you read it. The point he's making here is after 60 years, since 1947, the invention of hydraulic fracturing, we still don't really know exactly how to control everything or predict everything, but that's to be expected. Moving fast forward to 2009, another well-known oil and gas industry expert. Although our computing tools have improved, the supercomputers are a lot faster now. And if you ever go to a frac site, has anybody here ever been on a frac job? Okay. You'll notice that there's always going to be one van over in the corner, and inside that van are a bunch of computers and a bunch of people with MS and PhDs. And those computers are connected by satellite connection to Houston, where they have the supercomputers running, and they are running real-time computer simulations of the frac job as they're fracking. That's called prognosis, well prognosis. The idea is to predict what's actually happening down there, and by monitoring what you can at the surface, pressure, flow rate, you figure out whether what your computer model said should happen is actually happening. Okay. So after computing tools are improved as an industry, we remain incapable of fully describing the complexity of fracture, reservoir, and fluid flow regimes. So the point I'm making here is that, I'm making it over and over again, beating the proverbial dead horse, we don't know everything. The industry doesn't have complete control over what they're doing. They're working in a natural environment that is not inside of a building in an industrial zone. They're working thousands of feet underground where they can't see what they're doing, hear what they're doing, taste what they're doing, touch what they're doing, or smell what they're doing. They rely on models that are imperfect. The models are imperfect, and the information they feed into the models is imperfect.